The refraction of light leads to a number of other phenomena that you see daily. Remember the rhyme about the twinkling stars from your childhood?
Sure, I do.
Well, why do you think stars twinkle?
I'm not sure. I never really thought about it. Is refraction associated with twinkling of stars?
Definitely. The twinkling of stars can be explained through atmospheric refraction. Atmospheric refraction refers to the apparent random wavering or flickering of objects due to inconsistency in the physical conditions of the refracting media, such as air. In fact, atmospheric refraction can explain twinkling of stars as well as apparent sunrise and sunset. Let's first look at the twinkling of stars. Since our atmosphere is heterogeneous, that is, made up of many layers of various densities, the light reaching us from the sun or stars is refracted multiple times. As it crosses each medium, it refracts. Since these media or the layers of air are constantly moving, the angle of refraction of light is changing continuously. Therefore, we see the light from the stars flicker. In scientific terms, we refer to the twinkling of stars as astronomical scintillation.
That's very interesting. And what were you saying about apparent sunrise and sunset?
Well, not many of us realize this. But the fact is, we see the sun rise before the sun actually rises above the horizon. So, when we see the first rays of sunlight, we are actually witnessing an apparent sunrise. This happens because atmospheric refraction causes astronomical objects to appear higher in the sky than they really are. Similarly, sunset occurs shortly after the sun crosses the horizon.
How does this really happen?
When the sun is just below the horizon, its rays enter Earth's atmosphere and are refracted towards the Earth. The refracted rays reach us, making it appear as if the sun has already risen above the horizon. This is the apparent sunrise. The actual sunrise occurs when the sun actually crosses the horizon. Conversely, the apparent sunset occurs slightly later than the actual sunset. Since the light from the sun is already below the horizon, it refracts through the atmosphere, enabling us to see the apparent sunset even after the sun has already set. Now, another question for you. Can you tell me why the sky appears blue in color?
Well, that is the natural color of the sky, I guess.
If the natural color of sky is blue, then why does it appear red during sunrise and sunset?
I'm not sure. What's the reason behind it? Is it due to refraction of light as well?
Not quite. It's the result of scattering of light. Scattering of light is the deviation of light rays from its straight path. Almost all objects scatter light. That is, they reflect light rays incident on them. But some objects scatter light of some specific wavelengths, like the white ray of sunlight from the ventilator of your classroom or the golden hue in the forests. Light travels in a straight line as long as no object or particle obstructs its path. However, most media are heterogeneous, like our atmosphere, which is a mixture of gas molecules and other dust particles surrounding the Earth.
And as light propagates through the atmosphere, it travels in a straight path until it is obstructed by bits of dust or gas molecules, right?
You got it. Out of the 7 colors of light, blue has the shortest wavelength and therefore experiences more scattering than other colors. Therefore, the sky appears blue to us.
Very interesting. Are there other examples that show the scattering of light?
Sure. Scattering of light gives rise to many amazing and spectacular phenomena such as Tyndall effect, reddening of the sun at sunrise and sunset.
What is the Tyndall effect?
The Tyndall effect is the scattering of light by colloidal particles. Observe this narrow beam of light when I pass it through this colloidal solution.
Wow! I can see the beam of light passing right through the solution.
Yes, that is the effect of the scattering of light. When the beam of light is scattered by the colloidal particles in the solution, its path is illuminated. This phenomenon of the scattering of light is called the Tyndall effect. The illuminated path of the beam is called the Tyndall beam.
Is it only in colloidal solutions that we see the Tyndall effect?
No. You can observe the same even in air laden with dust particles, like in a dusty room. The Tyndall effect can also be observed when a fine beam of light enters a room through a small hole, such as an aperture in a ventilator. This happens due to the scattering of light by particles of dust and smoke in the air. Similarly, when sunlight passes through the canopy of trees in a forest, you can see the Tyndall effect at work again. The mist in the forest contains tiny droplets of water which act as particles of colloid dispersed in air. In fact, here's an interesting incident related to the Tyndall effect. London, in the summer of 1815, frequently saw prolonged and brilliantly colored sunsets and twilights. This was explained by the Tyndall scattering of sunlight by ash particles in the upper atmosphere. These ash particles were produced by the earlier eruption of the volcano Tambora. Now, look at this sunset. The sky has turned red.
Wow! What a lovely sight! You said that the red color of the sun at sunrise and sunset can also be explained through the scattering of light.
Yes. Let me explain. As the sun begins to set, light must travel farther through the atmosphere before it gets to you. Therefore, more of the light is scattered. As less direct sunlight reaches you, the sun appears less bright. The color of the sun itself appears to change, first to orange and then to red. This is because the short wavelength blues and greens get scattered. Only the longer wavelengths are left in the direct light beam, which is what reaches your eyes. Therefore, you see longer wavelengths and the sky appears red, pink, or orange. Can you recall any application which you can relate to the scattering of light?
I think I've heard about the red color used in danger signals, but don't know whether it relates to the scattering of light.
Actually, that's a very good example. Red has a longer wavelength and hence it is least scattered in any type of the atmospheric conditions. Due to this, the signal appears without change in color for longer distances. Therefore, it is effective to indicate the danger signal universally. This brings us to the end of this lesson on dispersion and the scattering of light. In this lesson, you have learned about refraction and dispersion of light through a triangular glass prism, formation of a rainbow, atmospheric refraction, and the scattering of light.